We will continue our discussion on auxiliary vector potentials, and today I'll show you how to construct solutions via this approach. So we would like to find the electric and magnetic fields given some source J and M. So what we do is we compute vector potentials A and F by solving the inhomogeneous wave equation and then use these longish equations to calculate E and H. Suppose we are working with source free region, that is J is 0 and M is 0. Then the equations, these two vector wave equations will reduce to del square A plus beta square A equal to 0 and del square F plus beta square F is equal to 0, where beta square is omega square mu epsilon. In rectangular coordinates, we can write A as a function of x, y, z. We can decompose A into three components. A, one along x direction, other one along y direction, one along z direction. Each of them ax, ay, az are functions of x, y, z. Now the del square A plus beta square A equal to 0 can be decomposed into three scalar wave equations, and this is possible only in rectangular coordinate system. If you go to cylindrical or spherical, it will be slightly different, so we should remember that. Similar approach we can follow for f as well, where f is a function of xyz. It's not given here, but we know that it is a function of space xyz. And similarly, we can decompose the vector wave equation into three scalar wave equations. If we are able to solve these six equations, we know ax, ay, az, fx, fy, fz. Therefore, we know both A and F. Then we are ready to calculate the electric and magnetic fields. That's the fundamental approach. Now let's look at this equation for electric field, and we will try to evaluate this, expand it basically. For this I need uh, the expansion for gradient of a scalar function psi in rectangular coordinates, and divergence of a vector quantity A bar and curl of a vector quantity F bar. Because I want to find out del dot A, which gives me a scalar quantity, I want to take the gradient of that scalar quantity, and similarly I want to take the curl of this vector quantity F. That equation, if you expand it, will look like this. This is one challenge that we always face. These equations turn out to be very long, and if I try reciting these equations, it will be very boring. But if I don't recite it, if I don't explain it, it may not be that obvious. So it is a very delicate balance I am going to be striking. For example, today I will show you one particular component, E ax cap minus j omega ax coming from here, and here I am going to be picking up the x component of the gradient of the scalar. If you look at del dot A, I have this equation here. I want to take the x component of it. That means I take the partial derivative of this del dot A with respect to x, which gives me del 2 ax by del x square, that term there, del 2 ay by del x del y, that term there, del 2 ax by del x del z, that term there. Now that is the x component of this. Similarly, I can write the y and z components. And for when it comes to del cross f, I use this determinant form to evaluate del cross f. So ax cap times del fz by del y, that term there, minus del fy by del z is that quantity there. Minus 1 by epsilon is coming from here. So can you similarly write these two rows down? I hope I have not made any mistakes in this. If there are, as usual, please let me know. I'll fix them. So H is given by this equation, which looks very similar to E. There's a lot of symmetry in electromagnetic theory. Now it's very obvious now. The moment we introduced the M and QMV, then Maxwell's equations became symmetric. The solutions also turn out to be very symmetric. And we can expand this also in the same form, and you can write it. That's fine. I'll leave it to you to figure it out. Now let's ask this question. can we write equations for TEM to Z mode? So TEM to Z implies both electric and magnetic fields are transfers to the Z direction. Z direction, the transverse implies Ez is 0 and Hz is 0. One of the ways to achieve this is if we choose Ax equal to Ay equal to Fx equal to Fy equal to 0, Az is not 0, Fz is not 0, and the partial derivatives of Az, Fz with respect to x and y are also not 0. If we make this particular choice, trust me, somebody said we get TEM to Z mode. So the question is, we want to verify. So where do we start? We start with the equation for E. And we now introduce this assumption, basically Ax, Ay, Fx, Fy, all zeros. The moment we do it, all of these terms will get cancelled off and we are left with a little smaller equation for E, which has three components, Ax, Ay and Az. But we want Ez to be 0. So Ez will be 0 if we choose Az of the form Az plus a function of x comma y e to the power of minus j beta z plus Az minus a function of x comma y e to the power of j beta z. This is the form we are going to be choosing. If we choose this form, then this quantity here goes to 0. Please verify that, convince yourself that it is indeed correct. Now, how about the H field? Exactly the same thing. We'll apply the same condition onto the H field and cancel off Fx, Fy or remove Fx, Fy, Ax, Ay from this equation, and we are left with reduced version of H. Once again, the Z component of H will be 0 if we choose Fz to be of this form here. We have equation for the electric field which has X and Y components only, because we have chosen Az to be of this form and hence Ez is 0. And we also have an equation for Fz. Now what we do is we will substitute the equation for Az and Fz in the equation for the X component of the electric field to start with. I'll do this one, we can watch me. Minus j 1 upon omega mu epsilon del 2 by del x del z Az is this quantity. If you differentiate with respect to z, we get minus j beta here and you are left with del Az plus upon del x, that's that one here. Az plus is a function of both x and y, therefore this, and it is derivative is not 0, therefore this exists, e to the power of minus j beta z, and derivative with respect to z here of this term gives me j beta and the remaining term is hanging out here. Then I'm left with minus 1 upon epsilon. Similarly, I can do for Fz and I get this term here. This we can simplify. Beta is omega square root of mu epsilon. Therefore, it gets simplified to this form here, which is basically Ex plus this quantity here plus Ex minus. One is propagating in plus x plus z direction, other one is propagating in minus z direction. Same exercise, please, I want you to do this to show that Ey is given by this result out here. Again, there is a lot of symmetry. Once you learn this symmetry, once you start observing the symmetry, after writing one, the second one you can simply rewrite it by changing the order of the symbols. Now, next we can do exactly the same process for the magnetic field. And we write the magnetic x component of the magnetic field and substitute Az, Fz, and we combine the terms into Hx plus component and Hx minus component, and similarly we write for Hy. Honestly, pause this video now. Time to pause and write these equations on a piece of paper. Please convince yourself that these equations are indeed correct. Okay. Now we have equation for Ex and another equation for Hy. The question that comes to our mind is, are these connected in any fashion or they're independent? Let's look at Hy a little closely. If I take out square root of epsilon by mu common out of this first term here, I'm left with is a quantity which looks like this. If you take out epsilon by mu square root of it from here, then I'll be left with 1 by epsilon, square root of mu comes out, and from here I'm left with 1 upon square root of mu epsilon. Similarly, taking out minus of square root of epsilon by mu from here, I'm left with this equation here. Look at this one. Compare it with this term here. It is exactly the same, which is nothing but Ex plus. And look at this quantity here. This term is exactly the term which is sitting here, which is Ex minus. Therefore, we can write Hy as square root of epsilon by mu Ex plus minus square root of epsilon by mu Ex minus, which is that term there, which is same as this term here, which is equal to Hy plus Hy minus. And we can define wave impedances Z wave plus and Z wave minus as Ex plus upon Hy plus or minus Ex minus upon Hy minus, and they will be equal to square root of mu by epsilon. I would like leave this as an exercise. Instead of choosing the previous combination for Ax, Ay, and Fx, Fy all going to 0, etc. If I choose Ax equal to Ay equal to Az equal to Fx equal to Fy equal to 0 and Fz not equal to 0, or Az not equal to 0 but all other components going to 0, prove that it also gives TEM to Z solution only. Similarly, you can also come up with TEM to X and TEM to Y modes also. You have to switch off a particular component, that is make a particular component a non-zero, switch on a particular component, or switch on a pair of components, and then you can get TEM to X and TEM to Y modes. Please do it. It's very interesting, quite you will develop a new feel for these results. Let us now find a solution which is transverse magnetic to Z, TM to Z solution. TM to Z by definition implies Hz is equal to 0. So this is obtained by choosing A as Az cap, Az a function of xyz. That means A has only a Z component and F is identically equal to 0. Az is obtained by the solution of del 2 Az plus beta square Az equal to 0, and we usually follow separation of variables method, where Az is represented as product of a function of x and y and z, independent functions, and we find the solution. When we go to the example, it will become obvious. Given after evaluating Az, the way we evaluate is the next step is to find out the electric field. That we substitute A and F in this equation and expand it to get Ex. Notice Ex has only Z component, Ex has contribution due to Az component because A has only Az component. And this is, can you visualize this straight away? Del dot A gives me del Ax by del x plus del Ay by del y plus del Az by del z. Since Ax, Ay are 0, we have del dot A has only del Az by del z. Yes. Now we are looking at the x component of it. So gradient of that is del by del x of del Az by del z, which gives me that result out here. A similar one will give me Ey, and Ez is a little longer because of minus j omega Az contribution coming here. If you take out minus j upon omega mu epsilon common, what we have is a little second order equation d2 by dz square plus beta square Az as Ez. How about H field? F is 0. Therefore, H is 1 upon mu del cross A, where A has only the z component, and therefore we can look in the determinant for the curl of A, we only have a z component, and Hx straight away is del Az by del y. 1 by mu is coming from the term which is there in the H expression. Hy is minus 1 by mu del Az by del x. Straight away evaluation, of course Hz is 0. Now the next question that we are going to ask is, Tm to x. I'm not taking it step by step. I'll show the whole slide one shot. This is very easy. If you want to get Tm to x, where hx is 0, we choose a is equal to ax cap ax. I want rest of the things to be done by you. Please verify that these equations are indeed correct. Why are we doing this? When you are trying to solve a problem, if I want to find out Tm to x modes of a particular problem, then if you have these equations with you handy, then it's very easy to calculate the electric and magnetic fields in terms of Ax. The process usually is, the moment I ask you to compute a particular solution to the wave equation, let's say Tm to x solution, you make an appropriate choice for A and F. If it is Tm to x, choose A equal to ax cap ax and F equal to 0. Solve this wave equation del 2 ax plus beta square ax equal to 0. I'll tell you the procedure next. That depends on the boundary, the geometry of the problem, etc. Once you compute Ax, substitute in this equation for E and H and evaluate the fields, and problem is solved. This particular field configuration is called a mode. So therefore this is called Tm to x mode. To compute T to x transverse electric to x mode, I choose F is equal to Ax cap Fx but A equal to 0 and solve for del 2 Fx plus beta square Fx equal to 0. Rest of the solution, writing the solutions is pretty much the same. So, but please do this once yourself. To do T to Z, yes, I choose F equal to AZ cap Fz and the process again exactly identical. Uh, though the method looks very straightforward, that's a beautiful part of it. Though it's very, at times, boring to see the same equation, that's the worst part of it. Unless you write it down on a piece of paper, you won't feel comfortable with it. So my request to you now is, before you go to the next video, stop here, write down the field equations for all these modes: Te to x, Te to y, Te to z, and Tm to x, Tm to y, Tm to z, starting from Maxwell's equation and remembering these two equations for E and H that are visible there. Take these two equations, rest of the thing you must write it on your own without looking at anything. That is how you develop the speed. Thank you.